In this video, we will be going over simple harmonic motion. We will look at springs, simple pendulums, and physical pendulums, and then do a practice problem to apply what we have learned. First, we will be looking at the position of springs when they are in simple harmonic motion. When a spring is pulled and released, its position with respect to time can be modeled by a sine wave. The amplitude of the sine wave represents the maximum displacement of the spring with respect to the equilibrium point. To start, we'll take a look at Hooke's law, which tells us that the net force on the spring is equal to negative kx, the spring constant times the displacement. From that, we can set negative kx equal to ma, and since the second derivative of x with respect to time equals acceleration, we can substitute it into our equation. We now have that the mass times the second derivative of x with respect to time equals negative kx, and when we divide through by m and rearrange the equation, we get that the second derivative of x with respect to time plus k over m equals 0. This is a second order differential equation. On the left, you can see that on the right, you can see that the equation that satisfies this differential equation is the x of t equals a cosine of omega t, because when you take the second derivative of a sine or cosine function, you get that function times a constant. Now we'll take a look at the total energy in a spring. Using our equations for potential energy and kinetic energy, we can substitute in values for x and v to find our total equation. The value of x is equal to a times the cosine of omega t. So when substituted in, our potential energy in the spring is equal to 1/2 k a squared cosine squared omega t. Likewise, the value of velocity is a times the sine of omega t. So when substituted in, k equals 1/2 k times a squared sine squared omega t. When added together, the total energy in the system is equal to 1/2 ka squared sine squared omega t plus 1/2 ka squared cosine squared omega t. We can pull out the 1/2 ka squared, and we get 1/2 k e equals 1/2 ka squared times sine squared omega t plus the cosine squared of omega t. However, if we look back to our trig identities, sine squared omega t plus cosine squared omega t is equal to 1. So our total energy in a spring reduces very nicely to 1/2 ka squared. A simple pendulum is modeled by as an oscillating, point-like bob suspended by a weightless string. The picture on the right serves as a great illustration of the velocity and acceleration of a simple pendulum in simple harmonic motion. For a pendulum to be in simple harmonic motion, the angle that the pendulum swings to must be very small. Since the angle must be so small, then we can say that tan theta and sine theta are approximately equal. Because of this, we can determine that the length of the pendulum over the displacement from the center is approximately equal to the mass times gravity over the spring constant times that displacement. We can determine this because L is the hypotenuse of the triangle, x being the opposite side from theta, is approximately equal to mg, which is the length from the top of the pendulum down to the intersecting line at L sine theta, using the force diagram, and kx is equal to the displacement of the pendulum using the force diagram as well. From that equation, we can multiply each side by x and divide each side by g to get that L over g equals m over k. From there, We know that omega is equal to the square root of k over m, and the period is equal to 2 pi over omega. So in other words, the period is equal to 2 pi times the square root of m over k. Well, we can substitute in L over G, and we get that the period of a pendulum in simple harmonic motion is equal to 2 pi times the square root of L over G. Also, if we want an equation for theta that satisfies its position in simple harmonic motion, we can get that theta is equal to the maximum theta that the pendulum swings to times the cosine of omega t plus phi being a phase constant, which is basically the original angle that we look at that the pendulum starts at.
A physical pendulum is a pendulum in which the mass is not concentrated at one point. This means that instead of considering force and mass the way we did for simple or ideal pendulums, we have to look at the proper rotational quantities, moment of inertia, and torque. From the equation, net torque equals moment of inertia times angular acceleration. For the pendulum shown to the right, we have the torque equal to negative mgh sine theta, where h is the distance from the top of the pendulum to its center of mass, and theta is the displacement in radians. Note that there's a negative sign in this equation because the angular acceleration of the pendulum opposes the direction of theta, which means that it will tend to accelerate back toward the center. Then substituting alpha equals the second derivative of theta, and for small angles theta, we have sine theta approximately equal to theta. We can simplify this much the same way we simplified for simple pendulums or for springs, and then it turns out that omega, or the angular velocity, equals the square root of mgh over I, and similarly the period is 2 pi times I over mgh. And this is based off the basic equation for a simple harmonic motion, which gives theta equals the maximum theta, or the amplitude, times cosine of omega t plus phi, where phi is just a phase shift constant. And note that if we substitute the moment of inertia of a simple pendulum into this equation, since we have I equals ml squared for a point-like mass, this just gives us the period for a simple pendulum, t equals 2 pi times the square root of L over G, which is as we calculated for the simple pendulum, so this is a valid equation. So now we have a problem to test our understanding of simple harmonic motion. An object of mass m1 equals 9 kilograms is in equilibrium when connected to a light spring of constant k equals 100 newtons over meters that is fastened to a wall as shown in figure A to the right. A second object of mass m2 equals 7 kilograms is slowly pushed up against m1, compressing the spring by the amount A equals 0.2 meters, as shown in figure B. The system is then released, and both objects start moving to the right on the frictionless surface. And then there are two parts to this problem. A, when m1 reaches the equilibrium point, m2 loses contact with m1, as shown in figure C, and moves to the right with speed v. Determine the value of v. In the second part, B, how far apart are the objects in the spring as fully stretched for the first time, the distance d shown in figure D. We can solve part A, which asks us to find the velocity at the equilibrium point by considering the total energy. Since there's no work done on the system by any external forces, U initial plus K initial equals U final plus K final, where U and K are the potential and kinetic energies, respectively. So in the initial scenario, which is shown in figure B, the system of the spring and the two blocks have potential energy 1/2 Ka squared. This is based off Hooke's law. And they have no kinetic energy since they're not moving. And in the final situation shown in picture C, there's no potential energy because it's at its equilibrium position, and we know that for a spring at its equilibrium position, all of the potential energy is converted into kinetic energy. And the kinetic energy at that point is 1/2 times m1 plus m2 times v squared, where v is the speed that we want. And at this point, since m1 and m2 are just on the brink of losing contact, they're still moving at the same speed, and they have to be combined into the kinetic energy. So solving this equation, we have v equals the square root of Ka squared over m1 plus m2, and this gives us 0.5 meters per second for the speed. Part B asks us to find the distance between block 1 and block 2 when the spring is fully stretched right of its equilibrium position. So there are two parts to this problem actually. First, we have to find how far right of the equilibrium position block 1 is, and then we have to find how far block 2 is. So to find how far block 1 is, we need to remember that this spring, since only block 1 is attached to it now, not block 2 as well, no longer has the same amplitude in its simple harmonic motion as it did in part B. Therefore, to find the new amplitude, we use energy the same way we did for the previous part, and we have ui plus ki equals uf plus kf, where the initial scenario is depicted in figure C, and the final situation is depicted in figure D. So in figure C, block 1 has no potential energy since it's right at the equilibrium position of the spring, and it only has kinetic energy, which is calculated as 1/2 m1 v squared, and we have v from part A, which is 0.5 meters per second. And in part D of this picture, the block is now at the furthest point right of the equilibrium position, so it has no more kinetic energy momentarily at a stop, and it has only potential energy, which can be expressed as 1/2 kx squared, where x is the amplitude of this spring now with block 1 attached, and it's the displacement from the equilibrium position to block 1's location in figure D. Substituting in the values, we get that x equals 0.15 meters. So now we just need to find how far right of the equilibrium position of this spring block 2 is. Now, for a spring, we have angular velocity, or omega, equals the square root of k over mass. And in this particular situation, we have k equals 100, and the mass that we're considering is just m1, because only block 1 is attached to the spring now. So we got omega equals 10/3, which means that the period of the oscillation of the spring with block 1 attached is 2 pi over omega, which simplifies to 3 pi over 5 when we substitute in the value for omega. Then, since in one full period of this simple harmonic motion, the block moves through its amplitude 4 times. This means that when it moves through just one amplitude, as in the situation between picture C and picture D, the time elapsed is 1/4 of its period. So now we know how long the two blocks have been moving for between figure C and figure D, and we know the speed at which block 2 was moving Since there's no other forces acting on block 2 now, it just maintains the constant velocity. And this means d plus x is going to be equal to the velocity of block 2 times the time it's been traveling for, which turns out to be v times t over 4, since, as we stated, it's been traveling for exactly 1/4 of the period of the spring in block 1. And this becomes 0.2356 meters. Now that we have d plus x and we have x, we can subtract to solve for d, which turns out to be 0.856 meters or 8.56 centimeters.